What's today? Hopefully Alyssa's here. How's everyone doing? Good. It's 8.3, I believe.
Oh,
Because we did. Oh, yeah, sorry. Okay, you'll notice one student is not a student. That's PK. He's here to watch me, not you. So don't get worried. Pretend like he's not here. Um, Hopefully Alyssa arrives. Otherwise, I'll be presenting Alyssa's work. Um, Give it a few more seconds. Did people finish that derivatives of the map? No. Okay. So we might do that at the end of today's lab section. Okay. Alyssa, I was just saying that we have one student who's not a student, but he's here to watch me and not you. So this will not affect your grade in any way. Okay. We're going to start today with second order differential equations. And let's see if I can get it here. Here we are. Do you have anything you want to show? Do you want to present from yours or do you want to present from mine? Okay. Okay. Why don't you pull up Zoom and then we can start with the text and then we can, when you're ready to share your screen, we'll share your screen. Okay, while she's doing that, what is a second order differential equation? Right, so conceptually, that's what it means when we're thinking about like spatial derivatives. Good. What does the word second order mean as far as the differential equation is concerned?
Initial,
What?
these two initials.
That when you're thinking about how to do it, yes, that would be the solution. You would need two initial things.
any equation with second derivative in it?
Second derivative, right? So the order of the equation, right? This is what order? First. This is what order? Good. This is what order? What? Nth, right, good. Are they inherently scarier? No, incorrect. They are the same. They are just as beautiful. So we often talk about them in the context of this one, right? What's this one? Acceleration, right? So we've seen this quite a few times. And today, wow, that was really good spelling. Today we're gonna see how to do this on the computer, right? How do we make the rocks think about accelerations? Alyssa, do you want to present from your desk or? You don't have to get up if you don't want to. Whatever's more comfortable. Okay. Nobody go to the next page or?
Put them into code essentially. Like by learning this,
we kind of already have the foundation base of how to do first order differential equations. So we're just gonna essentially put our knowledge from first order differential equations to second order. And with the textbook, it gives us the general form of a second order differential equation, which is equation 8.34. Essentially, this is showing us where x's are dependent variable, t's are independent variable, and then the d of x, dt's are first derivative. But since we're working with our second derivative, this could be as known as like an arbitrary function, or a nonlinear function, such as like the pendulum or harmonic oscillator. And the book was telling us that this is a given function that depends on x, the first derivative is time, but there was essentially a trick that we can use with this one is by defining a new quantity y, and that's equation 8.36. So this equation, you're essentially giving us the first derivative, dx over dt is equal to y, and then we can simplify that into our equation for 8.34, and our d of y over d of t equals the f of x, y, and t function.
Okay, so let's pause there for a second. Let's make sure we understand what's happening. So let me ask first a question. So here we have a second order in the derivative of x, right? But here I have x cubed. So does that make this a third order? No. Why not? Sorry, say that again? It's only the order of the derivative. But here I have two first order, like it's the first order squared. So is that a second order? No. Because essentially what we're saying here is that's essentially y squared, right? Not a new thing, right? This thing here, if we were thinking about it in the context of y, how would I write this? Yeah. Right? And that's what we say here. dy dt is f. dy dt is f. X, what's this thing in the middle? Good. T. You see how that's the same? That's through a clever trick. And can we do first order differential equations? Yeah, we've been doing them, right? We're experts at them now. We could teach a class on it. No, okay, all right. Go ahead.
Why did our d of y over dt change from the derivative of the second order? And it was
This one here? Yeah.
Like expand your derivative equation, you put the substitute y, and that's d of y over dt.
Yeah. Yeah, so for this one here, I mean, we could go through this and we could think about how this is rewritten, right? What would this part here be? dy dt, good. What's this first one?
Y squared over x.
Good. What's the second one? Good. What's the third one? What? That stuff. Yeah, good. That stuff. Right? And notice that that's all a function of x, y, and t. So we're good. Okay. Do you want to do higher orders or do you want to jump into the example? What's the vibe?
It's basically the similar trick as well as we did for the second order. So for the third order equation, where our d of x over dt and our second order differential is essentially going to be substituted by two variables, y and z. We have d of x over dt equals y, and then d of y over dt equals z. And then it's the same process as the first order. You're just going to substitute it, differentiate both sides, and then that's how you'll get your equation.
Good. Does it feel like cheating? Should kind of. It's like, I don't know, you took something that was hard and you made it easy, right? Now you know how to do it. So second order, third order, nth order, they're all solvable as long as you make what's called a coupled system of equations, right? And if you can solve a coupled system of equations, you're done. Okay. All right. What's up next? Yeah, yeah. Do you want to talk about the three-dimensional one, or do you have that different? Yeah. I don't think so. Okay. Huh. Did I? I don't think so. I don't think so. Yeah, Wednesday morning. Yeah, Thursday morning. It's not facilities? Okay, no, it's not facilities then. Yeah, okay. Cool, thank you. Okay, sorry, go ahead.
Placements of more than one kind of variable, or variables that we can vector through second order replacements and with a vector form. So this equation 8.41 is the right hand side. And essentially, we're still going to go through the same process as we did with the second order differential. We're going to substitute our variables into first order differential equations and have therefore we can solve it.
Right. Yeah, so hidden, right, of course, is the fact that this might be more than one dimension. Right, DR1, DR2, DR3, then you have three different S's. Cool. Okay, so let me let you share really quick and I'll put your screen over here. And just to clarify, which one is 8.5? This one up here? Here?
Yes.
Go ahead.
Start by defining our system with our first order differential equations. So we have the same setup of how we've been doing for our first order differential equations. The only difference now is that our f of x and f of y is what we're representing our d of x over dt and our d of y over dt in this situation. So we're taking our second order differential equations, we're substituting for our variable y and then putting it into our defined function. And then we're gonna have the same parameters from our starting time interval from 0 to 10, our number of steps, and then our end equation to return the number of step size. This the same order we've been doing for our first differential equations, where we have our key points, and where we're gonna arrange our each value for the number of steps. And we'll have our open list for to store our values for our function x of t and our function y of t. And then for that equation, we're going to have our R equals array, setting the initial conditions where our x or t equals 0, that's for our function of x and y, they'll be equal to 1. And then for our for loop, we're going to still do the same process and then get the run where we're solving our second order differential equations. But this time, our second order differential equations are now converted to our first order differential equations. So it's going to be the same process. We'll do the fourth order of the plata. So we'll be starting to evaluate our function FRT at our starting point, and then at the midpoint using K over K1, and then the same process, the midpoint using K over K2, and then our next time step using K3, and then finding the average where R plus equals all of that all together to find the average. And we'll show the star plot input of our function versus what it's.
Does this process make sense? We need to make a few clarifications, few modifications. So if we go back to the very beginning, yeah, here. So here, this is not exactly the thing that we just showed, that Alyssa just showed, deconvolving to second order equation, right? Because for f of y, that was the original, sorry, we had dx squared dt equals something. And then we said that dy of t was the derivative of that first thing, right? But here we see that this is an actual function. So instead, this is coupled first order equations as they normally are, right? And the simplification that we're going to make when we do a second order differential equation, like this one, is just to say that this first f of x, that's just y. Right? So yes, it's helpful to have these in here, right? These are going to be whatever initial conditions you're pulling out, but you're going to have a new term here that's just y. And it's going to feel redundant, but it won't be, right? And then on the bottom, the only one that matters, this will be the long one, right? So you've seen this before though, right? Because we just did this kind of similarly for the Lotka-Vatera equations, the foxes and the rabbits. But here now we're seeing that we can use a more complicated one. We just simplify this and we can use exactly the same formalism, right? Okay. Okay, any other issues? That was by the way, fourth order, not second, fourth, that's okay. Fourth order Runge-Kutta. Everything else is perfect. More advanced than the second order, obviously. So this looks good. What do I like about the code? It's all separated good. What else do we like about it?
Comments.
The comments are superb, right? Go down to the, right? So like this piece here, or sorry, before we go there, this piece here, right? Not just saying what f of x is, but what it represents, right? And then if we go down to the actual, this piece here, right? Maybe that's overkill. Maybe you're like such an expert, you don't need all that, but this could be really helpful if you're just forgetting, or it's been a long weekend and maybe you knock back a couple too many and you're like, what is the middle piece here, right? Does that make sense? Okay. Okay, and then for the very last part, so if I just scroll up a little bit, what am I going to complain about?
Plot.
Yeah, I just want the plot in its own box. That's perfectly okay for the example, but as we get larger and larger simulations, we make the data in a different place than we plot it, right? Okay, anything else? What's that now? That was it? Good. Okay, so let's go back here. Let me end this thing. Wait, no, I don't want to end the meeting. How do I do this? Oh, shit. Oh, yeah, I think you have to give up control, and then I can share again. Good. Okay, so let's have a look at what we're doing today, because I think that's the end of this, right? It really seems like a maybe an overly simple idea, but using it in practice is, I think, where we're going to get tripped up. Let's go to this. Yeah. Okay. Maybe we should have done 8.6. Maybe we do 8.6 today. We're going to do 8.2. I see. I see. Okay, so let's go through this example together. This one's not coded out, but I think it will be helpful. And what we're doing here is we're thinking about a nonlinear pendulum. So you have some pivot point. You have some, oh wait, let me share the screen. All right. So here you have some pivot point and you have a mass at the end of the wall. You've done this problem before? Okay, what does the pendulum do when I release it from here? With your hands? Just once? That right? Assuming there's no friction, you do this for ever. Does it ever get higher than the initial? No. So this is a really good way of making sure that our code works, right? Because if we can run the pendulum for a really long time and it does all the things we just said, like doesn't go higher than our initial, doesn't like become smaller with time, then we're capturing the physics, right? Okay, so why does the pendulum go down? Gravity, good. So let's see if we could look at the equation of motion for the mass. And we're going to write that here as L, the length, and the second derivative of the distance from, or sorry, the angular distance from rest, right? So if I go farther out, that's a larger acceleration, right? Okay. So let's go down and let's think about how these equations would be written. Here's the mass times the length and the angular acceleration squared. And that's due only to the fact that gravity is pulling down with sine theta, right? And we can show that geometry in a second. But you can simplify this and we can forget that all physics exists and we just have this, right? The second order derivative of theta is equal to something times sine theta, right? And so now in our heads, we're thinking about X's and Y's. Okay. So you could do that here. You can make that substitution on a piece of paper as you write this out before you start doing this, or you could do their substitution. They use omega just for clarity. Of course, omega is the angular velocity. So d theta dt, and then they write it like this. So here's our coupled system of equations, right? And if we went back to Alyssa's code, where do we make the change in order to solve this system? The what? I heard two at once.
I heard you. I said you could find one.
In the user-defined function? Good. Where in the user-defined function? Say that again. F of X and F of Y. That's it. Right? Now, of course, we need to fix the initial conditions, but everything else should be the same. Right? Okay. So that's where I think we're going to start today. Because you'll see that, you know, and this is sort of like what they say. They say the rest of the program is left to you. See exercise 8.4. And if I read today's agenda, I think we do 8.4 and 8.2, or at least we do them this week. So I think the best thing to do is to start with Alyssa's example, right? If you haven't coded that up already, let's build it, right, as a group. And then we are going to fit these ones in here. You do not need to use theta. You're welcome to. You're welcome to use omega, right? These would be the actual terms. But I want us to think that X and Y are not really X and Y. They are dependent versus independent variables, right? They are interchangeable. So we need to sort of separate ourselves from only thinking about them as positions. And similarly, Y being dx dt is not always a speed, right? It is just an intermediate step. So you can use whatever feels more comfortable to you and, you know, have a conversation with your partner about when you do that, but really try to take a step back from only thinking about X and Y in those terms, okay? Okay, and, you know, that kind of goes to this point of like, you know, we don't use F. It's written here in the book, but what do we want to write here? Function, real meaningful words. So if you decide, this is perfectly okay, if you decide to write the word, you know, like variable, or don't use the word variable, but something similar, and, you know, like intermediate step, that's okay. You just got to be consistent, right? Okay. Okay, we're running almost out of time here, but today's, let's see, where is it? Okay. Today we're going to do 8.2. I guess 8.4 is on Wednesday. Maybe we'll get to there quickly enough. Let's have a look at 8.2. Oh no, we already did 8.2. Is this out of phase?
Yeah, you guys.
Oh, okay. So let's start with 8.4 then. Because that is where I want it to be. Which is very convenient. So this is drawing on example 8.6. So again, find your partner, someone you haven't worked with before, ideally. If you've now run out of partners, I don't really believe you, but I could, I can be argued into that. So what you want to start with is start with 8.5. 8.5 sets it up properly. Make sure that it runs properly if you've never done that before. And then we'll transition it into 8.6. And then we'll do the exercise together. Okay? Questions? Comments? Concerns? Okay, break. No one gets to pick PK as a partner. Melissa's got free code. She's already done half of it. Bye now.